Hey everyone, hope you enjoyed your weekend. I sure did. This crazy weather we're having, it is freezing outside. And just last week, I bought all these bulbs to plant, and now the ground is frozen. But anyhow, hopefully, we'll get some better weather this week. So let's continue our conversation. I know we were talking about greenhouse gases, and we started with our free response question. I really think that we actually don't need to cover this much detail right now because in Unit 9, we go over the greenhouse effect again. But I think if I lay a foundation now, we could pretty much go over that quickly uh, later on. So the greenhouse effect is the driving force behind global warming, aka global climate change. Now, how does that happen? What occurs? Well, we need to know certain gases that are increasing in our atmosphere. And CO2 is big dog, but we all know that CO2 is pretty easy now, and sometimes it's isolated or disregarded in a free response because they feel that everybody knows that. Even elementary students know that. Not every elementary student knows that methane is also a greenhouse gas, or something like a CFC is also a greenhouse gas, or nitric oxide is a greenhouse gas. So that's going to take you a step above. Make sure that you're an AP student to know where those gases come from. We haven't even talked about where those gases actually come from. Most of them, and I'll just give you once again, just as this, some background, so you could get an understanding of how this picture works. CFCs are strictly anthropogenic. We used to make them. We have stopped making them due to something called the Montreal Protocol, which is basically a ban on the manufacturing of something called CFCs. So now we know that those are no longer a greenhouse gas, but they're very stable, and so they're still in our environment. I think it takes about 50 years for them to start to break down. So there is an estimation by 2050 that the CFCs would actually be disassociated in nature. So that happened. That's one source. Methane is another source of a greenhouse gas. Where does that come from? There's a big push right now saying cows are producing a large amount of methane, and that's true. Cows will produce some methane. Um, Another source of methane is going to be the decomposition of carbon molecules. If you have anaerobic respiration, which means basically the breakdown of organic material without oxygen, you're going to get as a byproduct methane. Methane could also come from landfills because all that garbage is rotting. It's covered with dirt. So all that stuff is decomposing on the bottom. This is going to release methane. Methane can come from sewage, as that starts to rot. Anytime you're going to see some rotting, you could pretty much produce some methane. We use methane. That's what's going to be coming out of our stoves. So it's methane in a sense. It's a good thing because we can use it as a fuel, but it's a bad thing if it just gets released into the atmosphere. Now, how does methane get out of the atmosphere? Well, methane does also disassociate in the atmosphere as well. Um, so if you were thinking of sources of methane, cows is going to be a good one. You could think of landfills would be a good one. You could think of wastewater treatment plants that have a lot of sewage could also be a big one. And when I say cows, we could throw CAFOs in there, that term, concentrated animal feeding operations. Wherever you have a lot of animals, you're going to have a lot of gas. But cows is the hot topic right now. So that's where those greenhouse gases come from. So once again, the greenhouse effect is going to occur, and your car is an example of a greenhouse effect. If you leave your car out in the summertime in the sun and you try to go inside of it, and let's imagine you had leather upholstery. When you get inside of it, the seat is going to be so hot. Well, what happened? The sunlight penetrated through, okay, and then it tried to reflect off of your seat, but it hit the top of your car, like another part, the ceiling of your car. It went through the glass, then went off the roof of the car, and then reflected back into the car. So the heat never got a chance to escape. So therefore, your car gets warmer and warmer. So we could take that same effect when sunlight penetrates through the atmosphere, then it hits the earth. Some of that's absorbed, some of that wants to reflect and get back out. But it's hitting this layer of gases in the troposphere called the greenhouse gases. And when they hit these gases, those gases get stuck and they come back down. And so they stay within the troposphere of the Earth insulating the earth, keeping the earth even warmer. So we need this greenhouse effect like we need a blanket. We need the right size blanket or we're not going to be comfortable. If our blanket is too big, then we get too hot, can't sleep. If our blanket is too small, then it's too cold, we can't sleep. We need the right size blanket to basically make sure that the organisms on our planet can survive. All right, let's continue here. So here is some data that's just going to show you uh, how our Earth is heating up. So this is some evidence of that the Earth is heating up. But I want you to pay attention to the timeline here. Okay, so we're from 1960 to 2010. But if you did do some research, and I'm not going to try to play controversy or anything like that. If you did do some research, New Jersey was part in an ice age. So if we took data, let's just say, I think it was 10 million years ago, and you could Google search that, our last ice age. If we had data from there and then we maximized a graph of just a specific time spot between 50 years, you would actually see a cooling cycle, right? So I want you to think critically, learn how to think critically. When a graph is being showed, try to look at the parameters of that graph. How long has that graph been, have taken data? You know what I mean? So you really need to see these, see the whole picture. There has been periods of global freezing and global warming and global freezing and global warming. I think that is non-debatable. What is debatable now is that the rate of the warming is increasing faster than it has before. I think that's probably the strongest argument that enthusiasts of global warming or supporters of global warming exist. So anyhow, there is some evidence that indicates that the Earth is heating up. All right. So let's look at some other data that may support this. Now, this is a famous graph. Famous graph. Make sure you look at it and understand it. This is the atmospheric carbon dioxide in Mauna Loa, Hawaii. What? Well, basically, we take this data as the most strongest data to indicate that CO2 is rising. Okay. Now, understand that there's going to be a peak and a valley, a peak and a valley, a peak and a valley in every year. Okay. And that peak and valley of every year is basically expressing the seasons. In the wintertime, there's going to be less CO2 absorbed. So you'll have a peak, a lot more CO2. And then in the summertime, a lot of that CO2 is basically absorbed because more plant life, more photosynthesis is going on. Anyhow, regardless of that, if we take the data from 1960 to 2010, we're going to see a really stark increase. Okay. And this is just some supporting evidence that indicates that. Look at the concentration. We're talking about 380 parts per million. Is that a very big concentration? Okay, we're talking about small concentrations. Remember, our huge atmosphere is about 80% and 80% nitrogen and 18% or 19% oxygen. The remaining 1% is mixed within those carbon dioxides, hydrogen sulfides, nitric oxides, all those other beautiful things. All right. So, yeah, I'm not just giving you how it is. Why Mauna Loa, Hawaii? Why won't we test it everywhere? Well, Mauna Loa, Hawaii is away from most civilization. I mean, it's an island, right? So it's away from a lot of industrialization. Imagine taking it in China or the United States where there's heavy industrialization. So you might get a skewed reading. They take these readings in Mauna Loa because it's away from industrialization. Also, there's big mountains. And if you Google search this or YouTube it rather, you would see that they take this on a mountain that's very, very high, almost at the border of the troposphere to the stratosphere. And I think they take it just directly right at the stratosphere. And so they say that the CO2 levels are more stable in that atmosphere. And they have this fancy machine that actually captures some air. You capture air in a glass jar, and then you put it through a machine. This machine gives you this reading. So they've been taking this data, and carbon dioxide is on the rise. Now, if we continue this, what we're going to see is a relationship between carbon dioxide and in our atmosphere, then we could see the carbon dioxide in our oceans, and then we're going to see that how that affects the pH in our ocean as well. So this is another very important graph that you want to become familiar with. Let's look at these numbers here. First off, we're looking at the time scale. Again, this is from 1955 to 2015. This is our pH scale. We got 803 to 833. All these are basic. So what are you talking about when you're talking about ocean acidification? Well, the ocean is becoming more acidic. It is basic. It is still basic, but it's going to become more acidic. And those changes in pH can affect a lot of organisms. Okay. So the red line is atmospheric CO2. We have that. It's on the rise. All right. And this is CO2 in parts per million. The navy blue line is going to be CO2 in the ocean. So we notice, oh, that's also increasing. Okay. And now we see the pH in seawater, and we see that's actually decreasing. I want you to become familiar with these type of graphs. They have two axes on the left and the right side. Okay. So this could be quite confusing. If I were to ask you, what is the atmospheric CO2 level? All right. And you told me if I asked you what was the atmospheric CO2 level in 2015 and you told me 8.23, I'm going to say, no, silly. You had to use this scale. So the atmospheric CO2 in 2015 is roughly about 400. If I asked you for the CO2 level of seawater, you shouldn't tell me in 2000, let's say 10, or this place right here, you shouldn't say 8.23. We'd be using this scale, which is about 380. If I asked you for seawater pH, now we're going to be using this scale. If I asked you for the seawater pH in 2015, you should say roughly about 8.05. Understand how to read scales like this. Very important. Let's continue. What can sunlight do? All right. Or what can heat transfer actually do? Okay. Sunlight or heat can travel three different ways. Okay. Radiation, and that's basically like it's transferring through a medium. Think of like these these rays just coming down. Conduction, and that's going to be the heat that's traveled when two things directly touch each other. Okay, so you think of fire on top of a pot, and the fire is touching the pot, and heat is transferring from the fire to the pot. That would be conduction. Radiation would be, let's say you just put your hands around the fire, and then you're feeling its heat. All right, and convection is going to be a different one. That's going to be the heat traveling through a medium. Okay, typically that could be a gas or that can be a liquid as well. All right, so when we talk about convection, convection is really those Hadley cells, the Ferrel cells, the polar cells. That's what we're really talking about, those convection cells. But right now, I want us to focus on radiation. All right, so let's think of radiation. And here is a vocabulary term. It's probably not on your homework packet, but I thought this would be a good place to put it. It's albedo, 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 albedo. I used to have a student named Beto, Brian Beto. He was a great kid. Albedo. This was a free response question, but I think we could learn a lot from it. Albedo is a term to explain or express the amount of sunlight that's going to be reflected back into outer space. So this correlates with the greenhouse effect. Okay. Now, I hope try to jog your memory. Maybe part physics, maybe part physical science. Now, things like if I wore a black T-shirt, and in the summertime, when the sun hits that black T-shirt, how does that black T-shirt behave? Does it reflect a lot of the sunlight, or does it absorb a lot of the sunlight? Well, a black T-shirt being a dark color is going to absorb a lot of sunlight. So I could do an experiment where I take one Viteri, put a black T-shirt on, another Viteri, put a white T-shirt on. And if I'm wearing that black T-shirt is going to absorb a lot more sun, and it's going to make me hotter. If I wore a fresh white tee in the summertime, that's going to absorb less sunlight, and reflect more. So you can think of it as if it's not absorbed, it's reflected. If it's reflected, it's not absorbed. Now the Earth can act like that as well. Okay, depends on the color of the Earth. What is the sun really hitting? Okay, now if the Earth has high albedo, that means it has high reflectability, meaning that a lot of the sunlight's uh, radiation is not being absorbed. In this example on our right here, we have polarized caps or a area that's covered with a lot of ice. It's white in color versus an area that is not white in color. Notice that it's saying 70% of the sunlight is absorbed. So that's holding in that heat. And about 30% is being reflected. Over here, opposite, 80 to 90, 85 to 90% is reflected versus 10 to 15, which is absorbed. What does that mean? Well, if the Earth is white, if it has more polarized caps, the polarized caps are nice and full, then that means a majority of that sunlight that hits that part of the planet is going to be reflected back into outer space. However, if our polarized caps continue to melt, then less sunlight is being reflected back into outer space and more is being absorbed because it's hitting the ocean, it's hitting bare land, right? So albedo is that term. Now, if the polarized caps melt and then more and more sunlight is being absorbed, this is going to gradually increase the temperature of our planet, causing global warming to even happen more. When a response occurs that makes it happen even worse, this is called positive feedback. If you remember, we went over positive and negative feedback cycles. All right. And this is albedo. All right. And I have this in here. I don't know why I have this in here, but I'm just going to continue with it. Dams are an environmental catastrophe, if you will. They're a good thing and a bad thing. Typically in nature, it's going to be a bad thing. All right. Why are they a bad thing? Because they kill fish. All right. They kill fish. They block migration patterns. All right. So fish like salmon are going to want to swim upstream to lay their eggs back where they had originally came from. But if they find this dam there, they can't go up there. So salmon and fish like sturgeon, which go back upstream to lay their eggs, they can't go back there, so they end up dying. It also blocks the flow of nutrient-rich sediment. So you can think of all these nutrients want to go somewhere, but they get blocked. And so sometimes all these nutrients are coming. I'm sorry, you don't even see my face. I don't know where my camera is. Imagine these nutrients are coming down from a river, but they get hit with a dam. So the nutrients stay in one section of that dam, causing eutrophication on one side. Also, that dam, where it's built, is going to slow the water flow on the other side and dry up that other region. Okay. Now, in order to save the fish, people have been creative, and we have developed some type of technologies. I think it's all fake, to tell you the truth. Uh, and it's called fish ladders. And so we build these on the sides of some dams, and the fish are supposed to swim up up these ways, and they're able to do so more so than let's say regular water. All right. Here is a dam, and on the left side here, that's where that NPK would build up because all that NPK would like to flow downriver, but it's not because it's being blocked by a dam here. However, why do we build dams? Well, we build them because we can get electricity from them, and that's a pretty cool thing, though. I'm not going to lie. And there's no CO2 being emitted during this formation. So how does that work? So we have a dam. Then we'll have an intake here. This water is going to flow. It's going to turn a turbine in a generator, and that generator is going to create electricity, and we could take that electricity and push it over there. The poor fish on the right side, though, can't go up here. The people who were dependent on that water flow now don't have water flow. So there's a pro and there's a con to dams. All right. However, sometimes we could build a fish ladder, and the fish could go back upstream to make it work. All right. I hope you'd enjoyed our